It is unsafe to ground one of the secondary legs of a transformer to create a neutral and use it for grounding purposes. Firstly, grounding one of the secondary legs creates a direct path for current to flow to ground. If there is a fault or malfunction in the transformer, this can cause a short circuit and pose a severe safety hazard. Secondly, most electrical codes require that the neutral leg of a transformer be connected directly to the equipment grounding system, not the secondary leg. Using the secondary leg as a neutral and grounding it violates this requirement. Thirdly, grounding the secondary leg does not provide a true ground reference for the electrical system. It creates a floating ground, which can lead to incorrect voltage readings and potential hazards. To correctly install a step-down transformer, firstly, identify the primary and secondary terminals. The transformer will have separate terminals for the primary, which is 240 volts, and secondary, which is 120 volts windings. Secondly, connect the primary terminals to the 240 volt power source. Thirdly, connect the secondary terminals by connecting one of the secondary terminals to the hot conductor of your load. Fourthly, create a neutral by connecting the other secondary terminal to a neutral bar or a separate neutral wire that is connected to the grounding system. Fifthly, ground the transformer case by connecting a grounding wire from the transformer's grounding terminal to the equipment grounding system. Always follow the manufacturer's instructions and electrical codes when installing a step-down transformer. Grounding the secondary leg of a transformer is unsafe, violates codes, and does not provide proper grounding. Use the correct method to ensure a safe and reliable electrical installation. Let's delve into the proper grounding and neutral connections for step-down transformer, focusing on safety and adherence to electrical codes. Understanding these principles is crucial for preventing hazards and ensuring the reliable operation of electrical systems. Grounding a transformer is a critical safety measure designed to protect both people and equipment from electrical faults. The primary purpose of grounding is to provide a low impedance path for fault current to flow back to the source, allowing overcurrent protection devices like circuit breakers or fuses to quickly trip and energize the circuit. This minimizes the risk of electrical shock and fire. The equipment grounding system consists of all the metallic enclosures, conduit, and other non-current carrying metal parts of the electrical system. It is connected to the grounding electrode system, which typically includes grounding rods, water pipes, or ground plates buried in the earth. The grounding electrode system provides a connection to the earth, ensuring that the entire electrical system is at or near ground potential. The neutral conductor, on the other hand, is a current-carrying conductor that provides a return path for unbalanced current in a 3-wire or 4-wire system. In a typical 120 volts/240 volts single-phase system, the neutral is connected to the center tap of the transformer secondary winding, providing a balanced voltage of 120 volts to each leg. The neutral is also bonded to the equipment grounding system at the service entrance, ensuring that the neutral and ground are the same potential. Now let's address the specific scenario of a 240 volts to 120 volts step-down transformer. As previously stated, it is incorrect and dangerous to ground one of the secondary legs to create a neutral. This practice can lead to several problems, including firstly, creating a direct path to ground. Grounding one of the secondary legs creates a direct path for fault current to flow to ground. This can cause a ground fault, which can trip circuit breakers or fuses, but it also increases the risk of electrical shock if someone comes into contact with a faulty piece of equipment. Secondly, code violations. Electrical codes such as the National Electrical Code or NEC and local amendments provide specific requirements for grounding and neutral connections. Grounding one of the secondary legs typically violates these codes, which can result in fines or other penalties. Thirdly, floating ground. Grounding one of the secondary legs does not provide a true ground reference for the electrical system. This can lead to voltage fluctuations and other electrical problems. To properly install a step-down transformer, follow these steps. Firstly, identify the primary and secondary windings. The transformer will have separate terminals for the primary, which is 240 volts, and secondary, which is 120 volts windings. The primary winding is the high voltage side of the transformer, while the secondary winding is the low voltage side. Secondly, connect the primary windings to the 240 volts power source. Use appropriately sized conductors and overcurrent protection devices to protect the transformer from overloads and short circuits. Thirdly, connect the secondary windings to the load. One of the secondary terminals should be connected to the hot conductor of the load, while the other terminal should be connected to the neutral conductor. Fourthly, create a neutral connection. The neutral conductor should be connected to a neutral bar or a separate neutral wire that is connected to the grounding system. This ensures that the neutral is properly grounded and provides a return path for unbalanced current. Fifthly, ground the transformer case. The transformer case should be grounded by connecting a grounding wire from the transformer's grounding terminal to the equipment grounding system. This protects against electrical shock in the event of a fault within the transformer. The size of the grounding conductor should be determined based on the size of the overcurrent protection device protecting the transformer, in accordance with NEC Table 250.122. For example, if the transformer is protected by a 20 amp circuit breaker, the minimum size of the grounding conductor would be 12 AWG copper. It is also important to ensure that the grounding conductor is properly connected to the equipment grounding system. This can be done by connecting the grounding conductor to a grounding electrode conductor, which is connected to a grounding electrode such as a grounding rod or water pipe. In some cases, it may be necessary to install a separate grounding electrode for the transformer. This is particularly important if the transformer is located in an area where the soil is not very conductive. When installing a step-down transformer, it is also important to consider the voltage drop. Voltage drop is the decrease in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. To minimize voltage drop, use conductors that are large enough to carry the load current. The size of the conductors should be determined based on the load current, the length of the conductors, and the allowable voltage drop. NEC Chapter 9, Table 8 provides guidance on conductor ampacity and voltage drop calculations. Another important consideration is the transformer's kVA rating. The kVA rating is a measure of the transformer's capacity to deliver power. The kVA rating should be selected based on the load that the transformer will be supplying. If the transformer is overloaded, it can overheat and fail. To determine the appropriate kVA rating for a transformer, calculate the total load in volts amperes and then divide by 1000 to convert to kVA. For example, if the total load is 5000 volt amperes, the appropriate kVA rating for the transformer would be 5 kVA. Additionally, consider the type of enclosure required for the transformer. The enclosure should be suitable for the environment in which the transformer will be installed. For example, if the transformer will be installed outdoors, it should be enclosed in a weatherproof enclosure. If the transformer will be installed in a hazardous location, it should be enclosed in an explosion-proof enclosure. The NEC provides detailed requirements for enclosures in Chapter 3, Article 312 and Chapter 4, Article 430. When working with electrical equipment, it is always important to follow safe work practices. This includes wearing appropriate personal protective equipment such as safety glasses and gloves, and energizing the circuit before working on it. It is also important to use properly insulated tools and to avoid working in wet or damp conditions. Before installing a transformer, always verify that the power is off and locked out. This prevents accidental energization of the circuit while you are working on it. Use a voltage tester to verify that the power is off before proceeding with the installation. During installation, make sure that all connections are tight and secure. Loose connections can cause overheating and arcing, which can lead to electrical fires. After installation, inspect the transformer and all connections to ensure that everything is properly installed and that there are no exposed wires or other hazards. Ground fault circuit interrupters or GFCIs are another important safety device to consider when installing electrical equipment. GFCIs are designed to protect against electrical shock by detecting ground faults and quickly interrupting the circuit. GFCIs should be installed in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. The NEC requires GFCIs in specific locations as outlined in Article 210.8. Surge protection is another important consideration when installing electrical equipment. Surges are transient overvoltage events that can damage or destroy electronic equipment. Surge protection devices, or SPD, are designed to protect against surges by diverting excess voltage to ground. SPD should be installed at the service entrance and any sensitive electronic equipment. The NEC provides requirements for surge protection in Article 230.67 and Article 285. Harmonic distortion is a phenomenon that can occur in electrical systems due to nonlinear loads such as electronic equipment and variable frequency drives, or VFD. Harmonic distortion can cause overheating of equipment, increased energy consumption, and other problems. To mitigate harmonic distortion, consider using harmonic filters or line reactors. The IEEE Standard 519 provides guidance on harmonic control in electrical power systems. Proper labeling and documentation are also essential for safe and efficient operation of electrical systems. All electrical equipment should be properly labeled with its voltage, current, and kVA ratings. Wiring diagrams and other documentation should be kept on file for future reference. The NEC requires labeling of electrical equipment in Article 110.21 and Article 408.4. Regular maintenance and inspection are essential for ensuring the continued safe and reliable operation of electrical systems. Electrical equipment should be inspected regularly for signs of wear, damage, or overheating. Any problems should be corrected promptly. The National Fire Protection Association, or NFPA, Standard 70B provides guidance on electrical equipment maintenance. In addition to the NEC, other codes and standards may apply to the installation of electrical equipment. These may include local building codes, fire codes, and environmental regulations. It is important to be familiar with all applicable codes and standards before beginning any electrical work. When working with electrical equipment, it is also important to be aware of the potential hazards associated with arc flash. Arc flash is a dangerous electrical explosion that can occur when there is a short circuit in the air. Arc flash can cause severe burns, blindness, and even death. To protect against arc flash, wear appropriate personal protective equipment such as arc-rated clothing and face shields. Also, follow safe work practices such as de-energizing the circuit before working on it. The NFPA 70E standard provides guidance on electrical safety in the workplace, including arc flash protection. In summary, proper grounding and neutral connections are essential for the safe and reliable operation of step-down transformers. Grounding one of the secondary legs to create a neutral is incorrect and dangerous. Follow the steps outlined above to ensure that the transformer is properly installed and grounded. Always follow safe work practices and consult with a qualified electrician if you have any questions or concerns. Remember, safety should always be the top priority when working with electrical equipment. Take the time to understand the principles of grounding and neutral connections, and always follow safe work practices. By doing so, you can help to prevent electrical accidents and ensure the safe and reliable operation of electrical systems.